So now we've seen that geometric series like that are divergent if the absolute value of the common ratio is greater or equal to 1. What if the absolute value of the common ratio is less than 1? Well, we're going to look at the sequence of partial sum because we want to see if we have convergence, in other words, if the sequence converges. So the partial sum starts with a, and then we add a times r, then a times r squared, and so on, up to a times r to the n minus 1. Now if I look at the same thing and multiply by r, by the common ratio, then a is multiplied by r, I get ar as the first term, ar is multiplied by r, I get ar squared as the second term, and each term like that is multiplied by r, and I end up with ar to the n as the last term. Now if I subtract the second line to the first, I get on the left hand side Sn minus r times Sn, and on the right hand side you see that all the terms cancel out except a in the top row and a r to the n, which I subtract, in the second row, so I get a minus a times r to the n. And now we can solve for Sn, and on the left hand side we have Sn multiplied by 1 minus r, and since we assume that the absolute value of r is strictly less than 1, in particular r is not 1, so 1 minus r is not 0, so we'll be able to divide. On the right hand side we have a multiplied by 1 minus r to the n, so dividing we get that Sn is a multiplied by 1 minus r to the n over 1 minus r, which makes sense because r is not 1. Now this r to the n, we've seen that when r is in absolute value less than 1, this goes to 0, and therefore the limit of the sequence of partial sum is a over 1 minus r, which means that a geometric series of first term a and common ratio r is convergent if and only if the absolute value of the common ratio is strictly less than 1, and in that case the sum of the series is a over 1 minus r, which you should think of as the sum is the first term divided by 1 minus the common ratio. So let's go back to the examples of geometric series that we have seen before. The first one was a geometric series with first term e and common ratio e over 3. E, the Euler number, as you know, is about 2.71. So it is in particular less than 3, which means that e over 3 is a positive number less than 1. So we have a common ratio here that is in absolute value less than 1. We can apply our formula. We get the first term e divided by 1 minus common ratio. And if I write the bottom as one fraction, I get 3 minus e over 3. So I can write that as 3e divided by 3 minus e. For the second geometric series that we had identified the common ratio as -2. This is in absolute value greater than 1, and therefore this series is divergent. The third geometric series that we looked at was a geometric series of common ratio 0.4, which is in absolute value less than 1. So we can apply our formula and we get the first term, which is 1 divided by 1 minus common ratio. 1 minus 0.4 is 0.6, which I can think of as 6/10. So the reciprocal is 10/6, which is 5/3. Now if we go back to rewriting as the sum of a geometric series, the decimal number 0.73, 73, 73, and so on, it is a geometric series of common ratio 1 over 100, which is less than 1 in absolute value. And therefore we get the first term, which is 73 hundredths, divided by 1 minus common ratio 1 minus 100. Writing the bottom as one fraction, we get 100 minus 1 over 100, that's 99 hundred. So we get 73 hundredths divided by 99 hundredths, that's 73 over 99. In other words, here we have written this decimal number as a fraction. In fact, the real numbers whose decimal expansion is either finite or periodic are exactly the rational numbers, in other words, the quotient of two integers. So if you have a periodic decimal expansion, you can rewrite that number as a fraction of integers. Now a few more examples before we turn to the next video. Let's say we're looking at the sum from 1 to infinity of -1 to the n plus 1 multiplied by 3 to the n minus 1 divided by 4 to the n. So we have power, so we may suspect that we have a geometric series, but we need to identify the common ratio in particular. So I can rewrite that looking at the fact that -1 to the n plus 1 is really the same as -1 to the n minus 1, and then I have two terms to the same power n minus 1. I can put them together and write it as -3 to the n minus 1. Then the 4 to the n at the bottom, if I want the same power, I'm going to write it as 4 times 4 to the n minus 1. And this way I can rewrite my series as the sum from 1 to infinity of 1/4 multiplied by -3 to the n minus 1 divided by 4 to the n minus 1. And then I can write this fraction as a power of a single number, namely -3/4 to the n minus 1. So now I have a geometric series in standard form and with common ratio -3/4. In absolute value, -3/4 is less than 1. That means this geometric series is convergent, and we have a formula to find the sum. Namely, it is the first term, 1/4, divided by 1 minus the common ratio, but the common ratio was -3/4, so when I subtract it I get +3/4. Now at the bottom, writing the bottom as one fraction, I get 4 plus 3, 7/4. So 1/4 divided by 7/4 is 1/7. Another example where we need to work out the formula a little bit to rewrite this as a geometric series in standard form. I have 3 to the power -2n that I multiply by 8 to the power n minus 1. I can write the 3 to the -2n as 1 over 3 to the 2n, and then 3 to the 2n is really 3 squared to the n, so it's 9 to the n. So I end up with 8 to the n minus 1 divided by 9 to the n. To have the same power, I'm going to write 9 to the n as 9 multiplied by 9 to the n minus 1, to the effect that I can rewrite this series as the sum from 1 to infinity of 1/9 multiplied by 8/9 to the n minus 1. So now I have a geometric series in standard form of common ratio 8/9, which in absolute value is less than 1, which means that this geometric series is convergent, and we have a formula for the sum, namely the first term, 1/9, divided by 1 minus common ratio. 1 minus 8/9 is 9 minus 8, 1/9, so we get 1/9 over 1/9, that's 1. Finally, another observation about this geometric series. If you look at the sum from 0 to infinity of x to the n, that's a geometric series of common ratio x, and therefore it is convergent if x in absolute value is less than 1, in other words, if it is strictly between -1 and 1. And in that case, we have an explicit formula for the sum of the series, which is the first term, that's x to the 0, that's 1, divided by 1 minus the common ratio x. Now you see that this gives you, if you think of the right-hand side, 1 over 1 minus x as a function of x, for x between -1 and 1, you get a series representation of the function. Right? You get this function that is far from being polynomial as something that looks like a polynomial with infinitely many terms. Right? You get powers of x, but you don't stop at a certain level like for polynomials, you keep going. There are many variants of that we can use, and this is something that we will revisit when we discuss power series. For instance, if I was starting at 1, Then of course the first term of my series, of my geometric series of common ratio x would be x, and then the sum of the series is x over 1 minus x, and you can think of that as representation as a series of a different function, x over 1 minus x instead of 1 over 1 minus x. Anyhow, we will revisit that, as I said, in a later module. But for now, we're going to focus on numerical series, and we'll see more on that in the next video.